Hi, this is Cassie Clifton. We're back with another episode of Geeks on the Beach. Here's Jansen and Grant.
Hi, how's it going?
Hi guys, want to learn about chi-square testing?
Okay.
Here we are.
So, you have three types of chi-square testing. You have a goodness of fit test, you have a homogeneity test, and you have an independence test. And the only difference between the independence test and the homogeneity test is your ho and your ha, which is your null hypothesis and your alternative hypothesis.
So let's get to talking about the differences.
Okay.
So, independence testing. Your null hypothesis is going to state whether there's an independent relationship between the two things you're testing.
What does that mean?
Independent,
Yeah.
They do not affect each other.
Oh,
they
okay.
have no effect on each other. Dependent is they affect each other and they affect the outcome.
And that's your alternative hypothesis.
Okay.
And an independence test is only for one population.
Whereas a homogeneity test is multiple populations, and the null hypothesis is just whether the different samples are equal to each other.
So all the populations are equal. But the alternative hypothesis is that all the populations are not equal. Alright, and then you would go into testing. And how you test for chi-squared is the sum of the observed values minus your expected values squared over expected values. Alright, and your degrees of freedom is your rows minus 1 times your columns minus 1.
And it's going to be necessary to create a table for both types of these tests.
Yes.
And to find the expected values, you're going to take your row total times your column total and divide that by the total of your whole table.
Alright, and before you start testing, you have to make sure it is safe to test. So you're gonna
Always
check
safe
your-
testing.
Yes. Yes. So you're always going to check your conditions. You're going to look for your expected values, which we just told you is that. It has to be greater than 5. And it has to be a simple random sample.
What
for
happens
you
if
to
that
test.
doesn't happen?
You need to,
Then you can either not test or proceed with caution.
but the AP exam, since we're all geeks here and we're all going to be taking the exam, we definitely should proceed with caution. And so if you're going to do this in your calculator, you're going to put your observed values in matrix A. You're going to hit stat, go to calc, and then hit x squared test, which is chi-squared. And then you're going to click on, you're going to make your matrix A your observed values, and your matrix B your expected values, and you're going to do the test, and it's going to give you a p-value and an x squared value, which you're going to create a skewed
Hey, Brody.
right
Hey, John.
graph. And with this graph, you're going to show the percentages of your p-value and your chi-squared value.
Awesome.
And the difference between the independence and homogeneity is in your conclusion as well. So you're just going to use your ho and your ha, and you're going to use that in your conclusion.
Alright, so our next test is the chi-square goodness of fit test, which Cassidy will tell you about now.
Yeah, the goodness of fit test measures whether a given distribution fits the observed distribution that you are given. So the ho and ha also measure this. So the ho would be if the distribution is equal to the given one, and then the ha would be if the distribution is unequal to. So it would be as if you're given a distribution of M&Ms or SAT scores from previous years, and you're trying to see if those distributions fit each other or if they're unequal, which would be the alternative hypothesis. So this is just really comparing the two and trying to see if they fit one another. You still use the same formula as you do with the homogeneity and independence test. It's going to be chi-squared is equal to the summation of observed minus expected squared over the expected. For degrees of freedom, you're going to want to make a table, so that way you can see all your values and plan it out. For degrees of freedom, it's going to be k minus 1, which will be the number of, say, colors or columns that you have for whatever you're using, minus 1. And for expected values, it's just going to be the number of your population, like the total number, times the percent that they give you. And they're going to give you that in the problem, like 30% red or 30% yellow. You just multiply that times the total number of M&Ms or whatever you have. And then also, like the homogeneity and independence test, the expected values all have to be greater than 5. And as with the other ones, you're still going to have a graph that's skewed to the right with your p-value to the right.
Since we've learned all about chi-squared testings, we're going to go ahead and show you how to correctly perform a chi-squared goodness of fit test.
As we saw before, a goodness of fit test measures how well a given distribution fits your observed distribution. So in this one, we will be measuring beach chair distributions. One in the sun beach chair sells an average distribution of 20% reclining, 10% deluxe, 40% basic, 30% lowrider. We were walking through the beach and observed 240 beach chairs. Types we observed are listed below. So we observed 45 reclining, 26 deluxe, 87 basic beach chairs, and 82 lowrider beach chairs.
So before we begin our test, we're going to go ahead and state our null and alternative hypothesis. So our null hypothesis for a goodness of fit test is whether the distribution is equal to the fun in the sun beach chairs. And our alternative hypothesis is whether or not the distribution is not equal to fun in the sun beach chairs, like percentages. So our conditions that we need is if our expected values is greater than 5, which we'll complete that later when we fill in the table. And the equation we're going to be using to find the chi-squared values is chi squared is equal to the summation of observed minus expected squared over expected. That's how we're going to find our chi-squared values. So we can go ahead and fill in our table because that's going to help us visualize what we need to be doing. So as we know, our observed here is going to be all of these. So we can go ahead and write those in.
45, 26 deluxe, 87 basic, and 82 lowrider. And that should add up to 240.
Because that's the number we sampled. So for our expected values, since this is a goodness of fit test, we're comparing the distribution. We already know the proportions of beach chairs that Fun in the Sun produces. So what we're going to do is we're going to take the percent and multiply it by our n, which is 240.
So we're going to do 0.2 times 240, which is our total population of interest, which is 48.
Sorry about this marker.
And then we're going to do 0.1 times 240, which will give you 0.4 times 240, -6. 0.3 times 240, which will give you our final total of 72. And all of these should add up to 240 as we're just taking the percentage and multiplying it by our observed values.
So now is when we can go ahead and check whether the expected values are greater than 5, which is our condition. And as we can see here, our expected values row is all greater than 5. So we can go ahead and continue on with the test. And, sorry about that. And the way we're going to go about finding our chi-squared value is by taking the observed number minus the expected squared over the expected. So that's going to be, I'm just going to do it
We'll
up
just,
here.
yeah.
45, we're just going to do an example of one, minus 48, and then squared over 48.
That will give you a value of 0.1875. And you'll go ahead and fill it in on your table. And you're going to continue this process for all of the 4 columns, and then you'll add them up to get the total, and also that will be your chi-squared value, which we did in the calculator, and we got a value of 2.586. Then to find the p-value, which tells you if you can reject or stay consistent with the null hypothesis, we're going to look at our Salmon table here, table C with chi-squared critical values, and we're going to find our value of 2.586. So we're going to look in the middle and look to see where 2.586 lies between, and it's going to fall to get a p-value of 0.459.
Since we have our chi-squared value, which is equal to 2.586, and our p-value, we can go ahead and create our skewed right graph. We're running out of room. But this is just a basic example example, and what you're going to do with this graph is you're going to shade in the p-value, which is going to be our 0.459, and you're going to write your chi-squared value down here, which is 2.586. And since we have a p-value of 0.459, we can go ahead and state our conclusion that it is necessary to stay consistent with the null hypothesis that the distributions from our sample is equal to the fun in the sun beach chair distributions. And we can conclude this because our p-value is greater than 0.05.
So our results aren't statistically significant.
It's Dominic the donkey, jingity jing, the Italian Christmas donkey. La 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 la.